Okay, so this video is on using the second derivative. The second derivative is great for determining the concavity of a function, and concavity is really just your function's personality. It kind of tells you how the graph increases or decreases. It describes the rate at which a function increases or decreases. Basically, if a function's derivative is increasing or f prime is increasing, then the graph of f is concave up. If a function's derivative is decreasing or f prime is decreasing, then the graph of f is concave down, and I'm going to show you what that kind of looks like. So in this picture, the top graph up here is actually the function. So this is f of x, and if you look in this region right here, f of x is concave down. It opens upside down like a frown. And in this other region right here, f of x is concave up. And if you look below, what we're seeing is a picture of the derivative. So this relative max is a critical value for f, and it happens when f prime is 0. At x equals 1, there's a relative min, which happens as also to be a critical value for f. So it happens when f prime is 0. And then in the region where the graph is concave down, basically from negative infinity to 0, our graph of f prime is decreasing. When the graph of f is concave up, our graph of f prime is increasing that whole time. So it just looks at comparing how the derivative is increasing or decreasing. So just to look at how we're going to figure out algebraically where f is concave up and concave down, what you need to do is find the second derivative. Once you've found the second derivative, you're going to go ahead and set it equal to 0 and figure out where it's undefined, just like we did when we used the first derivative test, and then we're going to make a number line for the second derivative. So the first thing I'm going to do is rewrite f of x. Because the numerator is just a number, it's just a coefficient, I'm going to write it as 6 times x squared plus 3 to the negative 1. So I'm going to go ahead and do the first derivative. I'm going to bring the negative 1 down, so I have negative 6 times x squared plus 3, this is the chain rule, to the negative 2, times the derivative of the inside chain rule here, 2x. So when I simplify this a little bit, f prime of x is equal to negative 12x times x squared plus 3 to the negative 2. And now that there's a function there, I'm going to go ahead and rewrite this back as a fraction. So I'm going to have f prime of x equals negative 12x over x squared plus 3 squared. So now I have to go and do the second derivative. So I have f double prime of x, and for this one I have to use the quotient rule. So the quotient rule is leave the lower function alone, so I have x squared plus 3 squared times the derivative of the top function, which is negative 12, minus, and now I'm going to leave the top function alone, so I have negative 12x, times the derivative of the bottom function, and I'm out of space here, so I'm going to just write it down here, times x squared plus 3, I bring the 2 down, sorry, and then times 2x, which is the derivative of the inside. Still chain rule applies there. All over, and then we have x squared plus 3 to the 4th power. I'm squaring that bottom part. Okay, I need to make this look a little nicer, so f double prime of x equals, and if I look at all three terms, because all three terms have an x squared plus 3, I can get rid of one of the x squared plus 3's. So I now have negative 12, there's still one x squared plus 3 left here, and then this becomes a plus sign. So plus, I have 12x times 2 times another 2x, and I end up with 48x squared all over x squared plus 3 to the 3rd. So f double prime of x I'm going to go ahead and distribute this negative 12. Ends up being negative 12x squared. Sorry, not plus, minus 36. Let me erase this. So minus 36, and then plus 48x squared, all over x squared plus 3 cubed. Okay, so simplifying just one more little bit, I have f double prime of x equals 36x squared minus 36 all over x squared plus 3 cubed. So this is similar to using the first derivative. We're going to figure out where f double prime of x is equal to 0 and where it's undefined. So f double prime is equal to 0 when the numerator equals 0. So I'm going to set the numerator equal to 0. So I have 36 times x squared minus 1, and I just factored out the 36 equals 0. So this happens when x equals plus or minus 1. And then I'm going to set the denominator equal to 0, so I have, so that the f double prime of x is undefined. So I have x squared plus 3 equals 0. Basically, this whole thing will be 0 when the interior function is 0. So basically, when x squared equals negative 3. So x squared will never equal negative 3, so this actually never happens. So we're just looking at when x is plus or minus 1. So if I go ahead and create my number line, I have on my number line for f double prime, negative 1, positive 1. And if I look in each region, I'm going to pick one number in each region to test in f double prime. So I have in each section a number before negative 1, so we'll do negative 2. Between we'll do 0, and after we'll do 2. And we're testing it into f double prime. So we have f double prime, and I'm going to write it as its factored form, equals 36 times x squared minus 1 all over x squared plus 3 cubed. So no matter what number I plug in into the denominator, because I'm squaring it, it's going to come out positive. So I'm only going to worry about just the numerator. So if I plug negative 2 in, I end up with a positive. If I plug 0 in, I end up with a negative. And if I plug 2 in, I end up with a positive. So here's what I know. In this region, f is concave up. F is concave down between negative 1 and 1. And after 1, f is concave up again. So I'm going to write my little explanation. F is concave up on negative infinity to negative 1 and from 1 to infinity because f double prime is, sorry, that S does not look right, is positive. And then f is concave down on negative 1 to 1 because f double prime is negative. Okay, sorry about my sloppy handwriting there. Okay, so that leads us to what is a point of inflection, and a point of inflection just happens anytime the graph changes concavity. So if I were looking at that last problem, the graph changed concavity 2 times. It changed concavity at negative 1 and at 1, so there would be points of inflection at negative 1 and at 1. So we're going to look at how to find the points of inflection of this function, which will be a little bit easier than the last function. So I'm going to start with find f double prime. So f prime of x is 4x cubed minus 12x squared and f double prime of x is 12x squared minus 24x. So I'm going to set this equal to 0. It's never undefined, and I'm going to factor out a 12x. And we have times x minus 2. So I get x equals 0, x equals 2. And then what I do is I set up my number line with both of these points, 0 and 2, just like we do with the first derivative. Then we pick one number in each region. So over here I'm going to pick -1. In between I'll pick 1, and after I'll pick 3. So I'm testing -1 into this function. When I plug -1 in, I get a negative times a negative, which ends up being positive. When I plug 1 in, I get a positive times a negative, which is negative. Again, I'm testing it here into f double prime. And when I plug 3 in, I get a positive and a positive, which is positive. So the graph changes concavity at both 0 and 2 because f double prime changes signs. So I can say f has a point of inflection at x equals 0 and at x equals 2 because f double prime changes signs at x equals 0 and x equals 2, period.